Hi, everyone. So this is a Capital One talk. Everyone heard of Capital One? To clarify, it's not Capital Radio or any radio station. It's who we are. We're a tech company that happens to do financial services. And we have a UK arm. And I'm from that part of Capital One. OK, so the title, From Fleeticide to Recovery, or When Your Auto-Scaling Policy Becomes Your Worst Enemy. I'll cover how we manage some of our service in AWS. I'll talk you through a real example of failure, and I'll show a simple demo, hopefully, that will show you some of the tools we can use to use effective scaling on AWS. The demo is a Spring Boot app, but it could be anything, really. Same principles hold. Anyway, enough of the spoilers. Let's define some of the terms to help us with this talk. Fleeticide. Anyone heard of that term? No? Good. That's good. Fleeticide is a term that captures at the event when all your tasks in your Docker fleet stop. Usually some form of cascading failure. Hopefully, I don't need to define the term recovery for anyone. Right? We're all used to services recovering, right? Oh yeah, and that confidential writer, given the nature of this talk, you can probably ignore that. First of all, it says we here, and it's only me. I'll get back to this in a second. OK, so we've got the problem statement, not promise of recovery, but what credentials do I have to come up here and talk about this topic? Well, I'm Steve Galbraith and I like coffee, but that doesn't give me the credentials for this talk. I'm a staff engineer at Capital One with a focus on site reliability engineering. I've had time in product development, identity and access management. I've done FX trading. I've done some space-related software for ESA, and I would play with computational fluid dynamics in the distant past as well. And I've been playing with Java for over 20 years. I've been at Capital One now for 11 of those years, and we really deserve our place in the best places to work. So come over to our display in the main hall and have a chat with us to find out more. Capital One takes SRE seriously. Most of our software spends most of its life cycle outside of the initial development phase. And hopefully that's also true for your software. But services have to keep up with what we discover and what makes code more reliable. And when it fails, it's our teams that recover service and hopefully engineer that failure point away. Yet, we code in our SRE teams. We don't just bump versions. That makes this area quite important for our customers, really. Well, it was supposed to be a joint talk. Jack is not able to make it today, so it is just me. But he's really helped getting this talk together, but he's not here. So I'm going to take the credit if the talk is good, and if not, it's Jack's fault, OK? And sorry, you're going to have to listen to my weird accent for the full duration. Let me start by setting the scene for what we do. We are out of our data center. All our services are 100% in the cloud. And that cloud provider? Well, it's no secret. It's AWS. The principles I'll talk about here, however, hold no matter what cloud provider you have. But for us, it is AWS. So some of the details may be a little focused on that particular cloud provider. So talking about that cloud provider, let's have a quote from Werner Vogels, CTO, recently retired, of AWS. Everything fails all the time. And if that's the Amazon CTO's opinion, it must be true. And then this next quote, that's me. Our primary goal is to provide service to our customers all the time. So, how do we make both those statements true? Well, like many things at AWS and other cloud providers, there are many things that need to come together to get things working smoothly. To ensure that everyone knows their responsibilities, AWS publishes a shared responsibility model which clearly shows what AWS will take care of and what's left for us to take care of. You'll often hear sound bites like, AWS will scale your services with demand to ensure availability, but this only works effectively if we keep our side of the deal. So they'll provide the compute, and we'll provide the queues and triggers for when we need more. At Capital One, we use a mix of compute options available in AWS, namely EC2, Elastic Cloud Compute, ECS, Elastic Container Service, and Lambda, in which you bring your own function. There's lots that goes into choosing the right compute for your workload, And there's no one answer to fit all, although we do love a Lambda, and we will use an EC2, but only as a last resort. Today, we're talking about our workloads that run on ECS. This is AWS's offering for running containerized applications. At Capital One, we specifically use the Fargate variant of ECS. So AWS handles the underlying fleet of services that run the servers, that run our applications. So what are the advantages of each type of compute? Well, we won't have time to go into detail here, but a mile-high summary for this, we can say that AWS provides more of the non-functional stuff as you move closer and closer to Lambda. So with ECS, AWS gives you the compute, you do the rest, including the OS. You support the whole lot, but they give you the compute. For Lambda, you just give them the function, and they do the rest for you. Scaling for load is included. However, you have to think a little bit differently about what you're coding and adjust your development model to suit the compute. ECS is the middle ground for us, and in this example that I'm going to talk about. You have responsibility for scaling and bringing your Docker image to the party, but they'll give you the rest and manage it all on your behalf. And you can keep your common development model, right? Let's face it, it's probably Spring Boot, right? That leads us nicely, at least I hope nicely, to the topic of what we need to do to scale effectively in ECS Fargate. So let's talk about your scaling options. There are two main types, vertical and horizontal. Vertical is a bit like the quote from Jaws. You're going to need a bigger boat. Just have the same number of tasks, but give them more capacity in each one. Horizontal is not that. You get more boats instead. Maybe more like Dunkirk, if I push that boat analogy to this limit. But both types are important. Horizontal scaling is what we are concentrating on in this talk. That lets us expand beyond choosing the right size, or in most cases, the wrong size. You have to choose for a maximum size of load. But Fargate has a range of options when it comes to horizontal scaling. At a fundamental, they're all based around the concept of setting up alarms that monitor metrics for certain conditions. Then you put in place some scaling policies, which run off the back of those alarms. For example, you could set up an alarm that runs off CPU. It's over a certain percentage, then you're going to scale up. You by adding a scaling policy that tells it to scale up. Whenever that ECS alarm triggers. Equally, what goes up must come down, and you can set the alarms and scaling policies to reduce the capacity when the opposite is true. So scaling is important in ECS to ensure that you get the right balance between ensuring customer availability while it's not wasting resources on idle tasks. This simplifies our job by allowing our services to find the right level of tasks that are required, rather than the development team continually performing a right-sizing exercise. So going back to the shared responsibility model, AWS provides the capabilities to scale, but you are responsible for configuring them appropriately for your application and your targets. So the AWS gives you the ability to scale, but you define and own the scaling policy. So that was the promise. But let's look at the situation when we, and I mean the developer we here, didn't meet that promise. This is a heat map of a service that failed in production. And unfortunately, I love a heat map. So a heat map is just a graph. In this case, it's latency running down against time. You see many pixels on here. Each is split into a separate bucket, and we count the number of hits in each bucket. This gives us a number that we can then use to color in a pixel. If the traffic is low, we give it a green color. Red is high, and the colors in between, well, you probably need to tell you, right? They're in between numbers, right? You can see different endpoints on this service clearly, but the different colors representing the amount of traffic in each latency bucket. The one that is super quick, if I can just come over here, this one at the top, super quick one, that is the health endpoint. I'll come back to why I point out the health endpoint, but it is important. On the left of the diagram, you notice that the service is happily serving customers over there. And you'll see on the right-hand side, also happily serving customers. But the bit in the middle, that doesn't look so good, does it? We're obviously not serving customers in that bit. And you can see a couple of attempts at recovery here. But this is all down to AWS doing the recovery stuff on it. This section here is one attempt at recovery. And here's a second attempt at recovery before service is actually then restored. Now, I couldn't tell from that service that was about to fail. Can you? If you looked at CPU and memory, you'd see a similar mystery to that one. CPU flat, memory flat. The service just stopped. So what happened to cause this Fleeticide? OK, that's that term again, Fleeticide. So let's talk about Fleeticide. Fleeticide occurs when a capacity issue in your service results in tasks being terminated and reducing the overall capacity. This reduction in capacity pushes more load onto remaining tasks, also pushing them over the limit, and they terminate before the first task has had a chance to restart. In our example here, we've got a pool of Tomcat threads. This is summed over all the tasks that we've got, by the way, which has reached its limit. And as a result, this particular application could no longer respond to health check requests, which means these instances were taken out of service, even though they were actively helping with overall capacity. Just to be clear, it's not AWS at fault here, it's us. We told it scale and CPU and memory limits and restart an instance if the health check didn't respond in time. Health check didn't stop here, it just didn't respond in time, it was just slow. So AWS stopped the task, brought in a new one, waited for it to be healthy before letting it serve traffic. But in the meantime, load switched to the reduced number of available tasks. Again, CPU and memory all still flat, so no scaling. The load hadn't dropped traffic, but moved on to remaining tasks. These reduced number of tasks, remember that new one is still not in service yet, it's still coming back to health. That triggered failure in the health check on one or more of the remaining tasks. Now that gets removed from service. So the more traffic moves onto the diminishing number of remaining tasks. And even when the new tasks start, eventually to take traffic, they immediately stutter to the pent-up demand for like everyone's still trying to get to your service. So that's cascading failure, and that is Fleeticide. So that is a policy that was originally intended to help with capacity in serving customer requests, has instead become our worst enemy here, and has taken away capacity, forcing the full fleet in that service to be terminated in a cycle until traffic reduces enough to let new tasks cope with that traffic. Those extra tasks you see in that task count are AWS bringing the new task to replace the old tasks that had just been terminated. Now, wouldn't it be great if all those tasks that were there were available to us to serve customers? If you would say yes, it would be great. Okay, fine, whatever. It's not interactive, fine, okay. Well, I didn't see the failure in the heat map. I'm sure you didn't see it as well. And for that latency data, we should have been fine. We had been beyond that traffic volume previously, and we hadn't deployed anything to that service to make it groan and start the Fleeticide nightmare. So what happened? OK, so that was the latency heat map. As I said, we could look at CPU and memory. Absolutely no indicators of the impending doom spiral. It was just seconds away. So it wasn't CPU, wasn't memory, not even volume of load. So, right. This is where I get nervous now, because I'm going to move towards a demo. So what I'm about to show you is not a production service for obvious reasons, but I'm sure it's code like you will have seen before. Hopefully not code like this, because this is just demo code. So rather than looking at the IDE to get the code, I've just done a simple screen grab of what's in this demo. We have a simple get endpoint. Well, we've actually got a couple of them. Calls a remote service with a Spring REST template. One gets information about a customer, and one that gets information about the balance for that customer. And then we combine them with some async calls to collect the results. Async, as we don't want our customer to wait for 2 wait periods when there's no dependency between the 2 results. We just want to call them together and click the result. So just ignore the very naive collection of the 2 JSON payloads into one join string at the end. That's not really what you do. You'd package it in the proper JSON though, but it's good enough for the purposes of this demo. Right, and then we deploy it. Right, for that we need a few Docker containers. We've got one for our Spring Boot app, one for a stub service that our Spring Boot app will call. We're using WireMock for this one. But I've delayed each response in that WireMock stub by 500 milliseconds to simulate some latency. Hopefully our real services are fast to 500 milliseconds, but whatever. Hopefully that makes it clear why we did this async join. Because for 500 milliseconds, the customer will be waiting a whole full second to get a response back, which isn't great. And finally, one for the rest of the AWS structure. We're using local stack here, which will act like CloudWatch for us. You'll find out why we use CloudWatch in a minute, hopefully. Right, so I've shown you some rather rubbish demo code. So it's demo time, right? So this is where it gets, hopefully, fun, if I can minimize that. Get up. Here's one I prepared earlier, hopefully. Run demo. Run demo, right? So here you can see the Docker container starting, normal Spring Boot app running, everything, I hope, ticking away in the background. Yes, everything looks like it's ticking away in the background. Right, let's pull in some other bits and pieces so we do our full reveal of what's going on. And that is way too large for that screen. We'll come back to that one. Let's connect it up now, actually. It's very hard with these weird... Don't get old. Glasses are rubbish. But I suppose the alternative's worse. We'll just keep an eye on that one. Well, that's not what I wanted to do, is it? Minimize that for now. Right, next one. Don't worry, this gets fun, don't worry. So that's our JConsole. Hopefully everyone's seen JConsole and stuff around. And then this last one is something we're going to do to push load through our service. Okay, so what does our service do? If I can find my mouse pointer again, get those back. Right, so as I said, we will, hopefully, as I said, there's one's got information about the customer. So there we go, there's our customer information. So first name is Steve, that sounds appropriate. And then we said about balances as well, right? So there's our customer's balance. I only owe £10, that's not bad for me. So that's pretty good. And then we're going to do one where we combine, as we say, we'll combine both those together into one response. Again, forget the fact that it's not actually well-formed JSON. Just being lazy and gathering those responses together. But you get the idea, right? So where's our load generator here? Let's knock that down. And let's start it off. So here we are running away at 1 request per second. Our latency is 500 milliseconds. That kind of makes sense, right? We had a 500 millisecond delay on the WireMock stub. So again, that makes sense that that's delayed by that much. Great, service is working fine. 1 request per second. Okay, let's move up to, shall we be brave and go for 2? 2 requests per second, nice. 500 milliseconds. Yeah, pretty cool. Happy with that. Happy with that. Oh, the big old 4 requests per second. What's going on here? 4 requests per second, yes. Oh my goodness, look. My latency now is starting to increase. Do you see that? That latency going up? That is not what we wanted to look at. So why is that? Well, CPU flat. Memory, normal Java sawtooth, right? Nothing special, so not CPU, not memory. And still, we're going up. So what could it be? Well, let's look at our M-beans here. Right, so here we have a graph of our, or about to be a graph, of our active threads that we've got on there. I was very lazy when I did that async join earlier. I didn't give it an executor pool, so it's just using Java's default fork join pool, which, for this demo, nicely limited at, well, pool size there is 4, right? So we're at 4 requests a second. The pool's full. Things aren't going well. Right now. Really bits my demo all over the place. This isn't good, is it? Okay, so if that combined one is struggling out at 4, let's reduce the load on that a little. So I can show you that that fork join pool drops again. Back down to 1. Response is now good. Go back to our JConsole, and our active threads in our pool is dropped significantly, right? So we're happy enough that reducing that has a direct effect on that number. So let's push load to a different endpoint. So the other ones didn't have that dependency on the fork join pool. So let's move to one of those. This is really awkward to look at this and run this, you know. And we'll start at where we left off in the other one. We'll start at 4 requests per second. Right, 4 requests per second. Now we're not combining the results. That fork join pool isn't constraining us anymore. We're doing it we're happily serving up our 4 requests per second that was previously causing us an issue. Okay, can we go higher? We can. At least I hope we can. If I can get the right number in here, let's stop that one. Should we go to 10? Should we go to 10 requests per second? Nice. Okay, so 10 requests per second. We're still all tickety-boo. Everything's all fine. But let's go up higher. Can we go 20? Again, look. We have this increase in latency. So we're at the limit of something, right? Again, we'll go to our JConsole. We'll look at our overview again to make sure it's not CPU and memory. I don't think 5% CPU is going to give us a hassle here. Our memory, as I say, normal sawtooth. So that isn't that. So what is it? Well, like all things, there is a constraint on this service, right? I said I was using a Spring REST template. I've just left it at default on there and using HTTP, Apache HTTP pool behind the scenes. You can see here by default, this is stuck at 10 in its pool. We've filled that pool up of 10 HTTP connections in that connection pool. So that is full, and that's our resource. Okay, so yeah, there we go. So let's have a look at it on this graph here. So what we've done, and what we recommend to do, is to look at all those software bottlenecks you have in your code and work out a percentage full. And this is kind of what we've done here. So this is the first example where we ran the fork join pool at 2, then we ran it up at 4, and then we ran it back down again at 2, if you remember. This is the pool sizing, so that's fine. So kind of ignore that one. And then this other section back here, where I'll get rid of this way of the projector, is where you'll see the Apache pool now actually being resource limited. So you can see those resource limits are actually giving us a bit of hassle. And now, hopefully, back to the demo. If I can work this one out. back away from the demo, actually. That's it for the demo. Hope that's it for the demo. I got away with that one, do you think? I think I did. Right. So, as we've just seen from the demo, bottlenecks can exist in software within your application, both in your own code and critically in libraries. Sometimes quite obvious when looking at configurations, but other times quite hidden. And you're relying on defaults you didn't actually realize needed to be altered. Limits can be both hard or soft. For example, with thread pool queue, a capacity might not necessarily block depending on your configuration, but instead offload your task to the calling thread. The application continues to work in this situation, but performance characteristics are likely to change, and it may not be immediately obvious why. There's not a definitive list of what these software bottlenecks are, but just try and think, anything has a size, what happens as that size limit is approached? So that really was a eureka moment for us. And it's easy to say after you've experienced the issues firsthand, but software bottlenecks should be treated just like any other bottleneck. If we monitor and scale based on CPU and memory, which we know can become bottlenecks, then we should also monitor and scale on software limits, as they too can become bottlenecks, as you've just seen in that demo. The traffic doesn't care if it's run out of CPU, or if it's run out of threads in a fork join pool or an HTTP pool. So how do we scale? First, identify your bottlenecks. Look beyond the basics. Publish the data for each bottleneck, so you know which one has caused the scaling event. Gather all your software bottlenecks into one simple metric. In our case, we've sought combined utilization. You saw me connect into that local stack in the demo and show you the combined utilization graph. And we dimension that by service name, so you know which service it is you're looking at. Then export that to CloudWatch. Now, because it's in CloudWatch, you can then set up your alarms and your scaling policy to scale appropriately, both up and down, based on the levels of those limits. So now it's not just CPU and memory, but you've now gone into software bottlenecks. But how do you go about getting observability in place on all those software bottlenecks? I mean, I can see CPU and memory ones directly from AWS metrics. But how do you keep track of those other software bottlenecks? Well, we do it by annotating our bean. With appropriate bean post-processing, obviously. We give it a meaningful name, which is the Apache pool that you saw on that demo. Now, we happen to use GemX for this, but you could use whatever works for you. Acrometer, OTel, well, we use GemX and OTel together. It's a bit complicated, but whatever. They're all good choices. Then you compute the maximum utilization based on all those software bottlenecks, and you publish that to CloudWatch as a CloudWatch metric, dimensioned by service name, as I said. That allows you to set up your alarms and scale in time before these bottlenecks start to affect your customers. Almost anything can act as a bottleneck. Look out for common ones. HTTP pools, you've already seen this. It's important to have a pool of connections around, as making those connections are expensive. So don't throw away your HTTP pools, right? Keep them there. But it is really important to manage them. Similarly, JDBC pools, right? They need to be managed in, if you're connecting to a database, you'll need a JDBC pool, right? That connection is really expensive. Make sure you pool them. But keep an eye on that pool. Queues, executor threads, you get the idea. The potential for you to introduce a software bottleneck in your code and affect your customer is almost limitless, even in libraries. So know what they use as well, be my tip. AWS SDK is an example where you have to start to think about how you're using that Java HTTP client and give it an appropriate size for how you're using it. So I don't know if you know, but if you just do you create your default SDK client on AWS, it'll use the Apache client by default, but with its default set up. And that's probably not right for your use case. So we know there's bottlenecks. We know they affect service badly whenever they hit a limit. So should we just up it to up to max? So if we see that resource to spare and it's just configurable limit, shouldn't we just increase that limit? Like Spinal Tap, like up to 11? Other numbers are available. But the way we see it is compute is cheap. Our customers expect 24/7, 365 uptime. It's better to work within known tested limits rather than push everything to the extreme. There are plenty of helpful techniques and formulas out there to help you find out how big your resource pool should be. Little's law on there? That's the little one? No? Okay. Tough audience. So Little's law is the L there is the average number of customers in a stationary system. Lambda is the arrival rate. And W is the average wait time and the customer spends in the system. That's really handy to start sizing pools. But these are all averages, right? Kingman's law, which is this more impressive looking formula over here, that provides the mass that describes that hockey stick figure that we're all aware of when we try and drive capacity to 100%. You find that queue time doesn't behave linearly as you push the queue, as you push all these resources to the maximum, especially when perturbations to average occur, especially as we get to 80% plus utilization. Anyone want me to find these terms? No? Okay, cool. There are a ton of exceptional talks on how to optimize, but that isn't the focus here. Instead, we're looking not to push limits of our hardware too much. Instead, we're going to scale before we push into that hockey stick inflection point in your resource bottlenecks. So keep that in mind when you're trying to bring a task back into service. It's got to be available before that inflection point is reached. So scale early, scale in time to allow that to happen. Compute is cheap, customer satisfaction is not. So let's look more graphs, right? Don't you love a graph? So let's look at one of our services. This is a happy path service now, with all this stuff implemented on, well, this particular service. This is it running over a couple of days. You can see the normal pattern for use, okay? So peaks during busy times, quiet in the quieter periods. Can't confirm or like what time this is, trade secrets. You can probably imagine that the quiet time is probably late at night. Maybe. So it's a stacked area graph of our services running multi-region. We do run multi-region. And underneath that, it's a graph of task count. Now, next to that, you can see combined utilization graph. This is our software metrics thing that we talked about earlier. Again, with task count underneath, it's the same task count in case you're trying to spot the differences. It's exactly the same. Just did that for reference, really. And you can see that as utilization drops, we drop our task count. And as load increases, the combined utilization increases, and we increase our task count. We've not had the schedule for this. Just does it. It means we don't have to find the right number of resources throughout the problem either. It finds its natural level. Okay, but Steve, that could have been predicted, right? So yeah, that one was a service behaving okay on average, but we can't rely on average all the time. As the name suggests, an average means that sometimes our resources will perform worse, sometimes better. This is why load itself is a trailing metric. Although it does drive the utilization of your resources, it's not the cause of your service running out of resources. That's solely down to those other resources in your application. You can easily imagine something you rely on being 10% slower than normal, just because stuff happens, right? So that means applying Little's law, that simple formula, and the number of customers waiting will increase by 10%. Then that can push our resource limit, and for the same node we had yesterday. Okay, and that's where Kingman's law starts to creep in, and we push that inflection point. Okay, so don't think that's quite true. How's about this? This is a more real-world experience. This is a different service entirely, hence the different colors. Maybe. But it's the same set of graphs as before. So throughput is the stacked area graph, and you see the combined utilization now on the other side. This time, something unexpected has happened. You can see clearly the different behavior with a very similar load in each region. The number of tasks in the green region there is much more than the blue region, despite them doing the similar levels of load. So this service had a connection to a JDBC pool, a database. The database in one region began to process its queries a little more slowly for the same input load as the other region. In this case, it was a maintenance task on the database that caused the region to behave outside of its average position. Stuff breaks all the time, right? But we didn't. We scaled in that region to ensure we could still provide service to our customers. Right sizing wouldn't have helped us here. Or even scaling based on that training metric of load. The load was exactly the same. If we hadn't scaled here, we would have been pushing that limits on that inflection point we talked about and getting towards that hockey stick failure in customer wait times. And maybe the retry loops as customers get bored of waiting for us to respond, and we're back into that Fleeticide behavior that we're trying so hard to avoid. Convinced? Yep, some nods. So hopefully you've seen our experience and why it's important to observe your software bottlenecks. Optimize the bottlenecks by all means, so you're not spending too much for your normal load, but don't over-optimize. You want a controlled failure point in your application that will lead any customer experience issues, so you have already scaled up before the detriment to the customer happens. Seems really obvious when laid out like this, but how many times do we assume that CPU load will be our scaling trigger without looking at what's causing the resource starvation on our service? Now, don't get me wrong, it still could be that CPU is your bottleneck, and when things behave in a normal window, it is more likely to be as that is where you've tuned to, but not whenever things go wrong and it drives those resources outside of that average position. But you can't stop at scaling. So going way back to that initial heat map, if you can remember that far back, our fleet of tasks got removed from service. Okay, it was not serving traffic well. The software bottleneck that was hit caused the health check to queue and fail, failing suddenly. So, was terminating the instance in that case the best we could have done? We're on message here with a green talk. Look, we've got Terminator slide in there. We need to distinguish between our service being in a death spiral that it won't recover from, in which case AWS will terminate it and bring back a new healthy one, and one that's just temporarily run out of resource. It's healthy, but full. Our terminator should leave the service up if it is resource restricted. It'll recover when the resource bottleneck eases. If we terminate in that moment of maximum stress, it'll transfer load to the remaining services and cause them to reach their maximum limit and get removed from service. We'll end up with a happy terminator, but unhappy customers. And we're in a spiral of a task destruction and remake until the load drops sufficiently for the tasks in that service to have enough capacity. Remember, this was our definition of healthy to AWS. This is our control. So something was there to ensure our services, yet again, ended up making our issue worse. Okay, we've got to take action, obviously. But what action do we take? Well, that's coming back to that important health check thing we talked about. So give them priority. Just like in our own lives, this is an important function, right? Everyone get a health check. Everyone make sure your service health checks well. Pay careful attention to what makes a service healthy rather than just busy. They are not the same thing. For example, perhaps put your health check in a whole entirely different servlet to remove them away from the noise of customer traffic. They deserve it. They aren't just something AWS makes us do. They're there to help us, along with AWS, figure out if we need a new task or if we recover by ourselves. So, I promised at the start of this talk that I'd leave you with 3 main takeaways. You've seen an example of production failure in one of our services. We've talked generically about what caused that failure and why we now keep a close eye on those resource limits, not just CPU and memory. And we've briefly touched on the importance of the developer experience in order to enable the tooling to do that in a readable, low-impact way. I've shown you how you can use those for effective scaling. That does work in production. I've shown you evidence of that working in production. Even when unexpected things happen. to move your response away from its average position. And finally, we've talked about how not to make matters worse, even when failure does happen. Remember Werner Vogel's all the way slide 2 or 3 or whatever, everything fails all the time. By making sure you distinguish a server that's healthy, but resource limited, and one that is not responding at all. So make sure if you are in that situation, make sure you keep as much resource around as possible to help in those high impact situations. Try and limit the impact of that terminator. So hopefully that fulfills the promise that brought you to this talk. I'm a little ahead of schedule, but that's probably a good thing. So that was our whirlwind tour today, hopefully giving you something to think about in your attempt to avoid Fleeticide and keep delivering customer experience in the way we want for our customers. Hopefully I've given you some insight into where bottlenecks can lie in a real application. Real, right? That Spring Boot app wasn't real, but you get the idea. Showing an actual customer experience failure. Those were real, by the way, those graphs we had up there, where we didn't have the correct recovery policy in place, and provided some tips to help you maintain the health of your fleet. Now I've got ages for questions if you want some, if you want to ask me some, or if you want to chat further, come and speak to us all at the Capital One stand. Okay, thank you. Any questions? Yeah?
So, let's say that you reach the limit of database connection pools, let's say 10 you have. So, maybe it might be a dumb question, but couldn't you, instead of creating an import, increase the limit?
Absolutely. So the question was, on that JDBC pool, instead of creating a whole new task to join the pod, could I not just increase the limit? And that's a fair comment, right? You can always push those limits up to the maximum. But then you're always looking for the right size. So what is that limit for that load? What is the limit for that load? I get next week, we do a very successful campaign. We push out to a lot of customers. 100,000 customers come in. On the back of that campaign, we expected 25,000. Oh, I didn't choose the right size. Not so good for our customer, right? So we've got the wrong size, they would queue and wait and enter a failure scenario. By doing something like this, you don't have to aim for the right size. You just kind of say, well, I want to go between this number of tasks and up to my maximum number of tasks and let it find the right size rather than you as the developer having to always choose the right size for that JDBC pool. That make sense? Cool. Any more questions? No? Cool. Well, thanks everyone for attending. Hopefully that was informative.